Hello everyone, and welcome back to this series on financial mathematics. Today we're going to be continuing our analysis of cash flows that is commonly encountered in financial products, and in particular we will be discussing two very important financial product structures known as annuities and perpetuities. So, what I have in front of you is just four mathematical identities associated to both finite and infinite series. Here we have a finite series starting at 0, ending at n, of another finite series starting at 1, ending at n, and then associated infinite series that start both at 0 and 1, and keep in mind those infinite series only converge for x between -1 and 1. So I won't get into why these are going to be useful quite yet, but eventually you will see how quite useful they are. So let us briefly review what is a cash flow. So a cash flow, keep in mind, is just going to be a sequence of, say, payments or compoundings that you might have on a particular financial structure. For example, if you have a loan, then you're going to be making payments periodically, say every month or every 2 weeks or something like that. So this cash flow can be represented as a sequence of payments, and let's assume that we make a payment at C0. Not common, but it is definitely possible, and another payment at C1, C2, C3, and so on, all the way up to Cn if it is finite, but it technically could be an infinite sequence of payments, right? So I'm just going to put that in parentheses, since that parentheses is not necessary in all particular cash flows, right? So let me give you a brief sequence of terminology that we're going to be using. So financial products that, let's use the word pay. Not necessarily pay, it could be borrowed depending on context, or it could be withdrawing or something like that. So what they're going to do is they're going to pay a series of cash flows over a predetermined time span. And that time span could either be finite or infinite. So the first category obviously would be a finite time span. So finite time span. So for example, for 5 years, for 7 years, for 2 weeks, and so on. And then an infinite time span. So when you have a financial product that pays a series of cash flows over a predetermined finite time span, we're going to be referring to that product as an annuity. And if that time span is infinite, we will be referring to that financial product as a perpetuity. All right? So let's just state out a very basic cash flow. For example, if our M value is greater than 0, with a sequence that looks like, for example, M, 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 all the way down to M, and let's assume that this occurs at t is equal to 1, 2, 3, 4, all the way down to 50, right? And it stops at 50, then what exactly is this product? Well, this is just an annuity, because it stops at a finite particular amount of time with constant, in particular 50 constant payments of size M, right? And this actually is called a constant or a fixed or a level annuity. So a constant, fixed, or level annuity. Now, constant annuities obviously are not the only type of annuity out there. So let me just mention a couple variations, and we're going to consider these variations in the future as well. So common annuity and also perpetuity structures, right? So the very first type of annuity structure that we obviously have is a constant or level payment annuity. And another type of annuity structure is called an arithmetic annuity. And another is a geometric annuity. And there's a few other common variations, but we'll discuss them at a later time, because these are the primary three that are commonly used. So what does a constant annuity look like, for example? Well, you could pay $10 today, $10 tomorrow, $10 the next day, $10 the day after, $10 the day after, and so on. So that would be a constant perpetuity if it were to continue forever. Arithmetic annuities, for example, let's assume it starts off at 10, then goes to 15, then goes to 20, then 25, and 30, and potentially so on. So when it's increasing by a fixed common difference, so an arithmetic series per se, then that is known as a arithmetic annuity or an arithmetic perpetuity. And if you have a sequence, for example, again, let's assume it starts at 10, and then it goes to 15, and then it goes to 22.5, and then 33.75, and potentially onwards. So you might be thinking, well, what exactly is going on here? So that's an increase of 50%. That's an increase of 50%. That's an increase of 50%, right? So arithmetic is an additive process, and here geometric is a multiplicative process. And keep in mind, if you don't remember how to view it as a multiplicative process, keep in mind 10 plus 50% of 10. This is just the same as 10 times 1 plus that rate of increase of 50%, right? So at least from the perspective of cash flows, that's almost like your alpha with an effective interest rate of 0.5. Right? So that's three common annuity structures: constant, arithmetic, and geometric, and also they can be from the perspectives of perpetuities as well. So in addition to the rate or the speed or the structure of the changes in the payments of an annuity, or moreover the time span of annuity, which could potentially be a perpetuity, you can also change the payments at current time options for that particular financial structure. So let me briefly go over what exactly I mean by that. So let's assume that we pay at the end of the time periods. So what exactly do I mean by pay at the end of the time periods? So let's assume that we have a timeline here. So let's assume that's 0, 1, 2, 3, 4. And let's take this from the perspective of, months, right? So it's possible that, 4 times 0 to 1, we pay at the end of the month. Here we pay at the end of the month. Here we pay at the end of the month. Here we pay at the end of the month. And that would continue all the way down, for example. So let's draw a longer, more general timeline. Right? So that will continue all the way down to the end of the last payment. Right? So this would continue onwards, and then all the way down to the last payment. Right? So note here that there is no payment at time t is equal to 0. So this type of annuity structure where you pay at the end of the time periods, this is referred to as an annuity or perpetuity immediate. An annuity immediate. So that pays at the end of the time periods. A slight variation of this would be what? So we can pay at the beginning of the time periods. So let's take a look at what the timeline would look like for that. Let's keep them parallel. So again, 0, 1, 2, 3, 4, all the way down to potentially the last one. So here, you're going to pay at the beginning of the month. Then that's going to cover 0 to 1. You're going to pay at the beginning of the month from 1 to 2, and then beginning of the month from 2 to 3, and then from 3 to 4. And that's going to continue onwards all the way down to the last interval for which there is no payment at time t is equal to m. So it's very important to see that both of these structures have end payments, but the difference is when they occur. So one is at the end of the month and one is at the beginning of the time periods. So this type, where it's at the beginning of the time periods, this is referred to as an annuity due. Right? So annuity immediate at the end, annuity due at the beginning. All right? So we should be able to see that this first payment here for an annuity immediate technically takes place at a time step before that time in the annuity immediate world. So it's pretty much a discounted version of the other, that is, the discounted version of the annuity immediate, is just equal to an annuity due. So we can actually state that from the perspective of discount factors or accumulation factors, depending on the direction. So we can say that an annuity due is just equal to a discounted annuity immediate, and also an annuity immediate is just an accumulated or reverse discounted annuity due, because they're obviously just reverses of each other. Right? So let's actually start doing a little bit of math, because this is going to be extremely important in the pricing of financial products. So we will only consider for today the following particular types of structures, where you have a constant value sequence. So C is equal to CK, where this is equal to M, all the way down to M, and potentially forever. Right, so we're only going to be looking at constant level annuities and perpetuities, and we're going to be looking at both the constant annuities immediate and the constant annuities due, and also the perpetuity perspective of those. So let's go back and refresh our memory of what we actually mean by present value. So the present value at t is equal to 0 for, let's assume that this is an annuity immediate, is going to be equal to what? So if we look at our particular timeline, so time t is equal to 0, 1, 2, 3, and so on, keep in mind the first payment occurs at 1, and then 2, and then 3. And keep in mind there's no payment at time t is equal to 0. So this first payment needs to be discounted once, the next needs to be discounted twice, the third needs to be discounted 3 times, and so on. So that means this present value, and keep in mind all of them are all equal to some value of m, that's going to be equal to a discounted value of m plus a discounted value of mv squared, and then mv cubed, all the way down to the last one, which is going to occur at time t is equal to n. So that's going to be m nu m. Right? So let's sort of verbally explain what we have here, is that we have n payments of size m. You could also say n equal payments of size m. So n equal payments of size m. So mathematically we can factor out m out of this expression, so we're going to have m multiplied by nu plus nu squared plus nu cubed all the way down to nu m, and we can express that in summation notation as just m times the sum from k is equal to 1 to n of nu to the power of k. And this is where you actually start to use those series representations. So this is just going to be equal to m multiplied by, so note that we do start at k is equal to 1, so that's going to be equal to m multiplied by nu minus nu to the m plus 1 all over 1 minus nu. And before we start to introduce some commonly used notation for this particular thing, I just want to mention just a brief bit of terminology. A unit annuity is where your payments, m, are all equal to 1. Because if you look at this particular object, this is actually a unit annuity. So if you know how to find the present value of a unit annuity, if your annuity is not constant, you can just multiply that unit annuity by the amount for which that annuity actually does compound on each of those particular points in time. So now let us introduce one of the very important notations that is used in financial products, and that is this little object, where it's the letter A, and then this little subscript has an end underneath like a half box where it's sort of missing the bottom and the left-hand side, and then we have the I letter directly next to that little half box. So what does this little object represent? So this represents the present value right? So it's a number of an annuity immediate, that is, the payments occur at the end of those time periods, with n payments, typically n is assumed to be finite when you use this notation, of size 1, so it's a unit annuity, with an effective interest rate of I. That's what the I to the right of it is, right? Because you can have a loan for different periods of time, different number of payments, and under different interest rates, right? And sometimes we would like to know the present value of that loan sequence. All right, now that we have this piece of notation that's very compact, that represents a very complicated structure, let's actually see what it is equal to, right? So A and I, the present value of an annuity immediate, will be equal to what? So by definition, that's just going to be equal to the sum from k is equal to n of 1, our payment size, times nu k. And we already know that's just going to be equal to nu times nu m plus 1 all over 1 minus u. Notice that we can factor out a nu out of the top side of this expression, so we can actually write this as just nu times 1 minus nu m plus 1 all over 1 minus nu. Since we're working under multiplication, we can group that orange term together if it makes us feel any better, and we can actually write that as nu all over 1 minus nu multiplied by the rest of it, which is 1 minus nu to the m plus 1, because technically that's over 1, but usually we don't write it. So once we have this, then you can be happy, but actually this expression is a little bit more complicated than we actually need it to be. So let's take a closer look at this expression that's in front of this more longer expression. All right? So what is nu all over 1 minus nu? So remember, nu, the periodic discount factor, is just the reciprocal of the periodic accumulation factor. So we can write that as 1 over alpha over 1 minus 1 over alpha. And what I want to do is I just want to put that over alpha to get a common denominator so I can subtract those bottom fractions. Once I do so, I'm going to have 1 over alpha all over alpha minus 1 over alpha. And then I can multiply top and bottom by alpha, and that's just going to simplify. So that's just going to give us 1 over alpha minus 1. But remember, alpha is just 1 plus the effective interest rate, so it's 1 over 1 plus I, and we still have that minus 1. And notice that those 1's cancel, so this actually just simplifies to 1 over I. Then we can go back to this expression and simplify it quite naturally. So what we have as a final result is that the present value of an annuity immediate will be just equal to 1 minus nu n all over I. And you could, of course, equivalently write that as 1 over I times 1 minus nu to the power of m. Right? So it's a very natural and beautiful result. So let's actually take this and extend it and consider another very similar idea, which is called a perpetuity immediate. So the only difference between an annuity immediate and a perpetuity immediate is that n goes to infinity. It's an infinite time span. So what is this? So this is going to be represented by a infinity I, because we have infinite number of payments. And by definition, this would just be equal to the sum from k is equal to infinity of 1 times nu to the power of k. So this is going to be equal to nu minus nu to the m plus 1 all over 1 minus nu, provided that n goes to infinity. But keep in mind that nu belongs to the interval 0 to 1. So this term just vanishes and goes to 0. So what you're going to have here is just nu over 1 minus nu, which we've already proven to be equal to 1 over I. Right? So we can easily show that the present value for a perpetuity immediate is just equal to the reciprocal of the effective interest rate. So that formula is actually very, very nice, right? So we have the present value of an annuity immediate and the present value of a perpetuity immediate. Now that we know how to value things in the present, let us move to the future and see if we can evaluate things there. So now let us see if we can find the future value of an annuity immediate, for which we're going to be representing as S, subscript, box n I, right? So the only difference between notation is that the A is now turned to S. So A, present value, S, future value. So this is the future value of an annuity immediate, so payments at the end of the periods, with n payments, because n is assumed to be finite here, all of size 1, so it's a annuity, a unit annuity, effective interest rate I, and the future value is taken to be at the time for which the last payment is actually posted to the account. So let us look at a timeline to sort of see how we will find the future value of this. So here we have 0, 1, 2, 3, all the way down to, let's assume, n minus 1 and n, for which that is the last payment. So the payments occur of 1 there, 1 there, 1 there, 1 there, 1 there, and 1 there, and 0 there. So notice that we're trying to find the future value at this particular time. So this particular value has its present value at time t is equal to n when we are there. But this payment of 1 needs to be accumulated once into the future. This needs to be accumulated twice into the future. This needs to be accumulated 3 times in the future, and actually n minus 3 times into the future. I noticed that I skipped a bunch of steps there. So n minus 3, n minus 2, and n minus 1, so alpha n minus 1 spaces in the future. And if we were to have a payment there, that would be pushed forward n points in the future. But keep in mind 0 times alpha n is still 0, so we don't have to consider it. So if we look at that, what would it be? So Sni will be equal to 1 times alpha to the power of m minus 1 plus 1 times alpha to the m minus 2 if we're sort of moving forward in time. And then finally plus alpha 2 times 1, and then plus alpha 1 times 1, and then finally we have 1 times alpha to the power of 0. That's according to that last particular payment. So notice that we're just going from 0, 1, 2, all the way down to n minus 1, so we can easily represent this in summation notation. So this is just the sum from k is equal to 0 to n minus 1 of 1 times alpha to the power of k, which is just going to be equal to, since we're starting at 0, we're going to have 1 minus, we're going to m minus 1, so that's going to be alpha to the m minus 1 plus 1, all over 1 minus that factor of alpha, which simplifies to just 1 minus alpha to the n, all over 1 minus alpha. Right? So we can actually make this a little bit more nicer. So we can write this instead, because alpha is just 1 plus I, so this is just going to be equal to 1 minus alpha n all over 1 minus 1 plus I. And notice that those 1's cancel and that negative distributes to the I. So it's just going to be 1 minus alpha n all over minus I. That negative is really easy to forget if it's just sort of hanging by itself. So what we can do is we can multiply top and bottom of this expression by negative 1 to get rid of that negative on the bottom. So what we have as an end result is that the future value of an annuity immediate at time t is equal to n with n fixed payments of size 1 under effective interest rate I, that little expression, will just be equal to alpha n minus 1 over I. Nice compact expression. Right? So let us just sort of summarize all of these mathematical results that we've built up to this point. So we have the present value of an annuity immediate is equal to 1 minus nu n over I. We have the present value of a perpetuity immediate is equal to just 1 over I. And then we have the future value of an annuity immediate is equal to alpha m minus 1 over I. So we have 3 very nice and compact forms. And this, again, is for annuity and perpetuity immediates, where the payments occur at the end of the periods with constant or level payments of size 1. So now that we understand how to formulate and work with annuity and perpetuity immediates, now let us shift our focus to how we deal with annuity and perpetuities due. So again, recall, what is the difference between an annuity due and annuity immediate? Annuity immediate makes payments at the end of each period, and an annuity due makes payments at the beginning of each of those time periods. So the very first payment is going to be made at time t is equal to 0. That's going to cover 0 to 1. Then we're going to have a payment at time t is equal to 1, which will cover 1 to 2. And that will continue 2 to 3. And then that as n minus 1, and then the last payment will occur at time t is equal to n minus 1, and will cover the last period with 0 value there. So again, from the conceptual perspective between annuities due and annuity immediate, this is again just a shifted annuity immediate. So let's see if we can perform a little bit of mathematics on annuity immediates. So what is the present value at time t is equal to 0 for an annuity immediate? This notation obviously isn't what we're going to have. So what is the notation for the present value of an annuity immediate under effective interest rate I with M payments? So this is going to be notated by A and I, but that would be an annuity immediate. So what we're going to do is we're just going to place 2 dots above the A. So this is the notation for the present value time t is equal to 0 for an annuity due, that is payments made at the beginning of the periods with M payments under effective interest rate I. So keep in mind that this has its own value time t is equal to 0, so we don't have to discount it. This is going to be discounted once, that's going to be discounted twice, that's going to be discounted 3 times, and that's going to be discounted n minus 1 times. So what you're going to have is 1 plus nu squared all the way down to nu n minus 1. So once we have this particular structure, and again this is for an annuity due, this is going to be equal to what in summation notation? Well, that's just the sum from k is equal to 0, because that's technically nu to the power of 0, up to the power of m minus 1 of nu to the power of k. So since we're starting at 0, that means it's 1 minus something on the top, so that's going to be 1 minus nu to the power of m minus 1 plus 1 all over 1 minus nu, and that's going to be 1 minus nu to the power of n all over 1 minus nu. Keep in mind, we can express the periodic discount factor in terms of the effective discount rate, 1 minus d, because remember, nu is equal to 1 minus d, where alpha is equal to 1 plus I. Right? That's the periodic accumulation and discount factors and effective interest and discount rates. So we can write that as what? So it's going to be equal to 1 minus nu to the power of n all over 1 minus d, where the minus changes to a positive, giving us a positive d value. So therefore, the present value of an annuity due and payments under effective interest rate I will just be equal to 1 minus nu n all over the effective discount rate. Right? So when we look at the perspective of the timeline, we can clearly see that annuity immediates and annuity dues with the same amount of payments under the same exact interest rate are very close to each other. So what is the mathematical relation between the present value ANI and the present value ANI double dot, right? So if we look at, for example, ANI, that's your annuity immediate present value, that's going to be equal to nu plus nu squared plus nu cubed all the way down to nu m. You should be able to note that nu is a common factor here, so I can actually factor that out. So I'm going to have nu multiplied by 1 plus nu squared all the way down to nu m minus 1. And you should remember that that's precisely equal to the present value of an annuity due. So this is just going to be equal to nu multiplied by the present value of an annuity due under the same exact number of payments and same exact interest rates I. So therefore, if A and I equals nu A double dot and I, that means I can multiply both sides by alpha, and that alpha times nu will be equal to 1. And then we can write that A double dot and I, the present value of an annuity due, will just be equal to pushed forward version of the present value of an annuity immediate. Right? So we get this very interesting property. Right? So that's for annuities due. What about perpetuities due? So for perpetuities due, what would that look like? So for perpetuities due, A double dot infinity I. So let's write that. So that's a perpetuity due. So infinite number of payments under some effective interest rate I, payments made at the beginning of each of these periods. By definition, that would just be equal to the limit as n goes to infinity of A double dot n I. Because we actually already know what A double dot n I is equal to, so that's just going to be equal to what? So that's the limit as n goes to infinity of 1 minus nu to the power of n all over d. We already know that nu belongs to the interval 0 to 1. That means this is going to vanish to 0, and we're just left with 1 over d. So therefore, we can clearly see that the present value of a perpetuity due will just be equal to 1 divided by the effective discount rate, right? And you might think, oh, this is actually pretty interesting, because if we recall what the present value of an annuity immediate is, that was just equal to 1 over the effective interest rate. So these are actually very, very related to each other, at least from the perspective of mathematics. A couple little exercises that I want you to try on your own, because these do have several applications that they can solve, is that the future value of an annuity due will be equal to alpha m minus 1 all over our discount rate, and the future value of a annuity due will be equal to alpha to the power of n of the present value of an annuity due, right? So we have a nice little formula for the future value of an annuity due, and also a relation between the future value and the present value of annuity dues as well, right? Now, one other mathematical thing that I think is very important, and before I actually state this result, I want to actually look at a couple timelines to sort of motivate their difference. So let's go again from 0 to n. So we have 0, 1, 2, all the way down to m minus 1 and n. So let's assume that I place a payment here, 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 and here, but I will not place a payment at n. So that's obviously an annuity due. So that's going to give me what? So n payments, so that's going to be a double dot n I, so present value of an annuity due. And I want to look at another timeline, again 0, 1, 2, all the way down to m minus 1 and n. And what I want is I want to not do a payment there, I want a payment there, 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 and I don't want a payment there either, right? So no payment at time t is equal to 0 or n. So what's the difference? So here, this is n payments, and this is n minus 1 payments, right? And technically speaking, I can view this from the perspective of an annuity. I could do actually an annuity immediate, couldn't I? Right? Because I'm technically missing either this or I'm technically missing that, depending on your perspective. But if I view this from the perspective of an annuity due, then the only thing that I'm really missing is this particular thing, and then they will match, right? So this object is just a n minus 1 I, right? So that's just the present value of an annuity immediate with n minus 1 payments, because the first is made at this particular time and it ends at this particular time. Because remember what an annuity immediate would look like for n payments. That would look like, if this is 0, 1, 2, all the way down to m minus 1 and n, if that's a ni, again, it's made at the end of the period, so we'd have that, and that, right? So the only difference between an minus 1i and ani is the last payment that occurs at time t is equal to n, right? So if you can look at this particular mathematical structure and connect between these two in particular, because these ones are obviously trivial to each other, then what we have here is that the present value of an annuity due with n payments is the same as the present value of an annuity immediate with n minus 1 payments, plus 1, which is that particular payment that is located at time t is equal to 0. Right? So we can clearly see that that's true from the timeline perspective, and I highly recommend try proving this mathematically. right? Because it mixes annuity immediates and annuity dues, and also the number of payments within each of them. Okay? So those are some of the mathematical principles and concepts associated to annuities and perpetuities due and annuities and perpetuities immediate. Right? We'll look at several applications of these financial products in the upcoming videos, so I hope to see you there. Take care.